Thank you everyone for coming to my talk. And today my talk is focusing on how we extract malware configurations from malware families. So a little bit about myself. I'm Mark, and I'm based in the sunny island of Singapore. So basically, to me, this weather is pretty cold. And I've been working with Palo Alto Networks for close to 7 years as a reverse engineer. And whenever I'm not diving down into the malware samples, I would just love to go for long jogs. So for my talk today, I'll basically cover a few things. I'll give a quick background information about answering questions like, for example, what is malware configurations and what is the value of malware configurations. But the main bulk of the presentation will focus on the techniques. For my talk today, I'll focus on GULoader and the various techniques they use to hide their configurations. Mainly two major techniques, ciphertext splitting and control flow obfuscation. And of course, we don't just talk about their techniques, but also touch on how we actually have defeat those techniques and we be able to extract out the configurations in an automated manner. So just for a quick background, like for those who are, just imagine with me, whenever we receive our new phones, the first thing we do is basically to configure our phone and put in preferences to it, and also maybe put in our contact list. So the same thing for threat actors, they will go about to purchase their malware, and the first thing they put in is basically information such as their C2 address, encryption keys, attack parameters, and various IOCs. This information is valuable both to the threat actors and also to the threat researchers. And the malware authors, like GULoader, knows it very well, that they need to protect this information. So therefore, they will put in a lot of anti-analysis techniques and various encryption in place to protect these configurations. Because this is the only one of the key ways that we can relate a particular, like for example, when we receive a hash, a sample, how can we relate this particular hash to a particular threat actor? So it's a lot based on the IOCs. So the malware authors would go about to protect these configurations. But for us, what we do is that we don't just extract it statically. We will execute it, and then we'll extract it dynamically, which I will go into more detail later. So this is just a quick overview of how we usually go about to extract malware configurations. So typically, we'll execute the samples inside our sandbox, and during the various phases of the execution, we will capture memory snapshots. So from the memory snapshots, we'll conduct post-processing. We have a series of memory snapshots. Then we'll run our malware config extractors against these memory snapshots, and then we'll be able to decrypt and obtain the configurations. And then given that we have obtained the configurations, we'll be able to index them and be helpful to the threat researchers to build a picture of exactly, like for example, they're interested in certain threat actors or certain malware families. So using these configurations, they will be able to do that. So what exactly is a GULoader? So it's basically it is a malware downloader. So for example, whenever threat actors they have access to ransomware or some form of banking Trojan, they want to have a means to be able to deliver this payload to the victim. And they know that the victim will likely be running some form of endpoint protection. So that's where GULoader comes in as a delivery platform to help evade endpoint protections. Once they execute on the target machine, they will call back to the C2 and download the payload. And something interesting about GULoader is that it's basically a very big piece of shellcode running inside the GULoader sample. And the authors of the GULoader always upkeep their code, and they constantly make it harder and harder for us to analyze their samples. So let me just make use of this timeline diagram just to give an overview of how GULoader has been evolving. So just a quick check, back in 2020 when it first started, some of the research done by CrowdStrike have shown that actually you could just quickly do a search for the substring HTTP. You'll be able to obtain the C2 URL, which is the most important part of the GULoader. But what we are interested in is basically what GULoader did in the past few months from late 2022 all the way to the recent times. So in the recent times, the authors of GULoader has actually improved upon their techniques, and they make use of ciphertext splitting and control flow obfuscation to protect their configurations, which I will share more in detail. So whenever we have a malware configuration that we need to decrypt, we need to basically have 3 pieces of information. We need to be able to identify their encryption routine. We need to be able to obtain their encryption key, and of course the ciphertext itself. So only given these 3 pieces of information, then can we obtain the configuration. So for GoLoader, they are pretty interesting. They actually maintain a consistent use of just the XOR. Maybe it's for the ease of their implementation of their code. And of course, given that their shell code is very challenging if they were to implement some AES encryption algorithm in there. So they choose to make use of the simple XOR. And the other thing about them is that the location of the encryption key seems to be pretty predictable. So we can make use of a Yara rule to obtain the key itself. But what is interesting over here is that GoLoader actually put in a lot of effort to protect the ciphertext itself. So for the first technique they use is what we call as the ciphertext splitting. So basically ciphertext is just a string of bytes, which is the encrypted version of the plain text, which is the C2 URL. So what it does is that you split up this bunch of bytes into multiple dwords, each dword 4 byte long. And after that, given this 4 dword, they will run it through a series of arithmetic operations, like for example, XOR, add, or sub. So something to note here is that every single one of these dword is being encoded using a different sequence of arithmetic operations. So that makes them pretty unique. And then finally, each one of these dword is actually stored in a function as a local variable. So given this technique, so basically it's very challenging just to go into the memory to just look for the ciphertext, because they are all split up and they are all stored inside a function as a local variable. So they are not like a blob of data inside, like for example, in a dot data segment and things like that. So this is a call graph. Call graph, on the left, you can see the call graph basically have a sequence of instruction beginning of how they decode the first dword of the ciphertext. And this is just only the first dword. So in order to decode the first dword, what GoLoader have to do is basically have to first read out the 4 immediate values over here, and then run it through a sequence of mathematical operations, which is basically, in this case, it's a 2 XOR and finally a sub. And then you can obtain the first dword. The first dword is very critical to obtain, because the first dword basically tells us how long the entire ciphertext is. So as you can see over at this corner, it's basically just a general idea of how large the function will be. So basically you have to execute the entire function in order to obtain the ciphertext. So, but that's not all that the GoLoader authors actually does. They actually, on top of that, they actually make use of control flow obfuscation. So previously we see a nice looking call graph with a nice function in there, but when that's because I have already removed the control flow obfuscation. So on top of the ciphertext splitting, what GoLoader did is basically they actually made use of control flow obfuscation. In this case, the example, what I was showing here is that they basically littered CC bytes, or basically init tree, all over the instructions. And then after the CC byte, they append with a series of junk bytes. So when you load GoLoader code into IDA, basically all you see is a lot of junk and a lot of instructions mixed together, because IDA could not tell which is data, which is code. So this makes the analysis of GoLoader very challenging. So how do they go about to do it is basically, if you look over here on this diagram, so this is after I beautify the code and make it easier to read. So you have an init tree, which is basically the CC byte, and then after that you append with a series of junk bytes. So this is how they implemented one form of code flow, control flow obfuscation. Basically, whenever there's a CC byte, they will trigger the breakpoint exception. On top of that, they have an additional exception, set of instructions to trigger another exception. It's basically the SS violation exception. So as you can see, a series of instructions over here, all it does is to basically make ESI equal to 0. And we all know that when we try to write into the address 0, what you result is basically access violation. So two exceptions over here that bootloader made use of to achieve a control flow obfuscation. So my initial idea is basically very simple. Why not we just find all the various patterns, like for example, the CC byte is CC, and then the various combination of instructions that give us access violation, and we find and replace them. And then to jump over the jump bytes, we replace it with a short jump. So that is my very initial simple idea. And yes, it is possible. I could do that. Basically, I could beautify the code from the left and obtain the function on the right. That is what I did initially. But what happens is that I came across a bootloader sample that was being uploaded to VirusTotal just a few months back in May, and I noticed that there's something else they did. So on top of the original two exception, now they introduced a third exception, basically a single-step exception. So to achieve single-step exception, what they did is that you need to enable the CPU thread flag. So they have a series of instructions to enable the CPU thread flag, and as a result of the thread flag, the single-step exception will be triggered whenever the thread flag is being enabled. So at this point, it's actually impossible to go about to make use of the simple idea of just trying to find all the combinations of all the instructions that will trigger the three exception, and then try to patch them and replace them. So yeah, this technique doesn't work anymore. But of course, there is a solution to it, which I will share. But before I could share the solution, I need to go into a bit more detail of exactly how bootloader implemented the exception handling code. So this is a pseudocode of the bootloader's handling function, which I will step into more detail. So the first exception they will have to handle is basically whenever there is a CC byte, it's a breakpoint exception. So and the authors bootloader are very careful. So they will check to make sure that their code is not being debugged. In this case, hardware debug. So they know that their code will get analyzed by researchers and malware reverse engineers that use debuggers. So the first thing they check for is hardware breakpoints. So whenever there is a use of hardware breakpoint, they will crash the execution of the sample. So if there is no hardware breakpoint, they'll continue to the next step, which is basically they'll read out the byte right after the CC byte, which is actually the encrypted offset value. Basically, this offset value is the number of jump bytes that's being appended after the CC byte. And they will decode it using a single byte key. And then on top of the hardware breakpoint, now this time he will try to look for software breakpoints. And because, again, they are being very careful, making sure that there is no debuggers around. So if there is no software breakpoint, they will now add the offset value back into the instruction pointer. Basically, the idea is that we want to move the instruction pointer away from the original CC byte to the instruction after the sequence of jump bytes. And then they'll return the execution back to the code. So other than handling the exception of the breakpoint, they also have to handle the exception of single step and access violation. So basically the code is very similar to the previous version, the previous exception breakpoint. The only difference is basically the location of where that encrypted offset value. So instead of the immediate byte after the CC byte, this time is 2 bytes later. So that's the difference. So previously I mentioned that single byte key that is required for us to know exactly how many jump bytes to jump over. So and bootloader being very careful, again, they hide this information using something that we have previously seen, basically a sequence of instructions, arithmetic instruction, in this case, XOR, and add. Then you get us the single byte key when this sequence of instructions is being executed. But this sequence of instructions are not consistent. That means every single sample, you will see a different sequence of instruction being there. So after executing this sequence of instruction, we'll get us the single byte key, and then we could be able to tell how many bytes of offset value to jump over. So all in all, basically, this sample of bootloader made use of ciphertext splitting and then 3 different exceptions in order to carry out its hiding of its configurations. So what can we do about it? Previously, I mentioned the use of find and replace. We know that it's impossible because there's just too many combinations. So what we did is that we made use of CPU emulator, the unicorn framework, and a set of ERR rule. So what we did is that we know that the sample we have already executed using our sandbox, and we have a sequence of memory dump. So we will have a first Java rule to locate exactly where that function that contain all the D words is located. So next, then we have another Java rule to locate that single byte key. So 2 Java rules, and then finally we could emulate the entire function using the CPU emulator. But of course, we need to also implement the handling code, exactly how GoLoader did it to handle the 3 different types of exception. So this is how we did it in order to extract the configurations from GoLoader. But the interesting thing is that the authors of GoLoader continues to improve upon their code, and they have more tricks up their sleeves. And just when I was just still doing preparing for today's talk, and I realized that there is an even newer variant of GoLoader that was being uploaded in August. So there is an additional trick there being used by the authors of GoLoader. So instead of the original 3 exceptions, this time they added 2 more exceptions, basically illegal instructions and privileged instructions. So a total of 5 different exceptions. This time, additional 2 more. So what happens is that given these 2 additional exceptions, it basically breaks our config extractor again, because now we have to add in additional code to handle 5 exceptions instead of just the original 3. So not only that, the other thing they did was that they actually made an interesting change. So for one of my Java rule, in order to obtain that single byte key, that sequence of instructions to give us the single byte key, I rely on an important offset value, which is the offset value of B8. So whenever an exception is being triggered, basically the Windows context structure will need to be read. So we'll read basically the B8, which points to the instruction pointer where the exception is being triggered. So usually we always see this B8 instruction being in the code itself. So my Java rule was written around the presence of this B8 value to locate the instructions that give us the single byte key. But GoLoader again increased the challenge. This time they also hide the value of B8 itself in a sequence of instructions. So as you can see, the B8 no longer is easily obtained from just a Java rule alone. So it breaks our existing Java rule. So all in all, this new sample of GoLoader not only have the additional exception handlers, we have to make changes to our Java rule in order to again automate and to extract out the configuration of the GoLoader. So in summary, it's basically this is a continuous cat and mouse game between researchers and the authors of GoLoader. So, but being able to combine the use of Java rule, CPU emulation, and scripting, we will continue to be able to extract out malware configurations from malware samples and malware families. So, and in fact, for those who are interested in a lot more detail, because I could only cover in this talk mainly GoLoader and basically the more interesting aspect of it, in our paper, together with my co-author, we actually put in code snippets and a lot more details for how config is being protected in the other families like Trickbot, Emotet, Redline, and Warzone Red. So do check out the paper. And thank you.
Thank you.